In this video, we're asked to measure the charge to mass ratio for electrons by running them through cyclotron motion. So I actually took the specifications for this device from a popular commercial product. I think my numbers are pretty close here. And we have an accelerating potential of 300 volts for the electrons. We're going to run those electrons into a magnetic field with a strength of 5.84 Gauss. That's perpendicular to the velocity of the electrons. And the radius of curvature is observed to be 10 centimeters. What I'm asked to find here is a formula for E over m in general, so the charge to mass ratio. And then we're going to plug in all the numbers from our experiment and get a numerical value for the charge to mass ratio for the electron. So we begin by looking at the accelerating potential, that 300 volt potential, and I want to have a symbolic name for that, and it's just another capital V. And we can use energy conservation to figure out how fast the electrons are popping out of that. And just as a magnitude here, the drop in potential energy for the electrons as they pass through this potential difference is given by the magnitude of their charge. We'll call that QE, times the size of the potential difference, that's V. And that drop in potential energy goes into the kinetic energy of the electrons. And I'm taking care to make my little v for the speed a lot smaller than the big V for the potential difference. And then I analyze the cyclotron motion part of the experiment. And in cyclotron motion, we have the Lorentz force on this moving charge, providing the centripetal force. And so I can start by just writing down sort of generically Newton's second law for this cyclotron motion. And it might be nice to visualize my electron over here and the force on it pointing to the center of curvature. And if we use the right hand rule on this for the Lorentz force, we point our fingers in the direction of V, sweep out to the direction of B. Our thumb points away from the center of curvature here, but it's a negative charge, so our force points back toward the center of curvature. The magnitude of the Lorentz force is given by QVB. So I have the magnitude of my charge, and there's V for the velocity, B for the magnitude of the magnetic field. And then the mass we're dealing with is the mass of the electron, and then the centripetal acceleration is given by V squared over r, where r is that radius of curvature for the path of the electrons. So one factor of V is going to cancel. And so now it's a matter of putting these two things together and finding a solution for the charge to mass ratio. So I'm going to go ahead and solve for V in the second equation and then plug that into the first equation. And when I solve for V in that second equation, I just multiply both sides by r and divide by m. Now I plug that into my first equation, and I'll go ahead and square everything in those parentheses. And I can go ahead and cancel one factor of QE on the left and right, and I can cancel one factor of ME on the top and bottom on the right side there. And I notice that I get a QE over ME, in other words, the charge to mass ratio. So part of the whole point of this is just to illustrate how the charge and mass are tangled up, and why in the early experiments on the mass of the electron, there was no way to resolve this. You just end up with a ratio of the charge to mass instead of being able to directly measure the mass of the electron. That's why Millikan's oil drop experiment was necessary. So I'm going to isolate the QE over ME on the right hand side. I'm multiplying by 2 to get rid of the 1/2, and then I need to divide by the B squared R squared. And I end up with this simple general solution. 2 times V, that's the accelerating potential, over B squared times R squared. So now we're ready to plug some numbers into this. Just a quick reminder, my magnetic field was given in Gauss, and I have to change that to Tesla, and that's a factor of 10 to the 4th. So I get 0.000584 Tesla. So Teslas are the bigger unit by a factor of 10 to the 4th. And the charge to mass ratio for the electron to 3 significant digits comes out to 1.76 times 10 to the 11th coulombs per kilogram. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.